Welcome to this explainer. Today, we're diving into a genuinely fascinating journey. We're going from the absolute brute force of the rig floor right down to the surgical precision required to navigate miles underneath the Earth's surface. We're breaking down the anatomy of the drill, looking at the raw mechanical reality and the just incredible technology that makes modern offshore drilling possible. Here's our roadmap for today. We'll cover the drilling cycle, optimizing drilling parameters, the bottom hole assembly, steering the wellbore, and finally, geosteering and real-time data. Let's jump right in.
Section 1. The drilling cycle.
To really wrap our heads around this, we have to establish the physical baseline first. The sheer mechanical reality of drilling. Everything else we'll talk about is built on top of this fundamental process. Drilling operations actually follow a surprisingly simple, well-defined sequence. You drill ahead, you stop to make a connection by adding another joint of pipe, and then you drill ahead again. That's it. This simple rhythm is literally the heartbeat of the rig. But here's the catch. Managing this cycle, and specifically managing the interruptions to it, is exactly what dictates whether a multi-million-dollar well is completed on time and on budget. So the absolutely crucial point here is that stopping the drill bit to replace equipment costs immense time and money. To put that into perspective, imagine what's called a trip. This means pulling the entire drill string out of the hole just to change a bit, and then running it all the way back in. It's a massive undertaking. Pulling out of a 4,000-meter hole requires unscrewing and racking over 400 individual pipe joints. Even when the crew is moving at top speed, this single interruption takes anywhere from 8 to 16 hours. Every single trip heavily impacts the bottom line. Section 2. Optimizing drilling parameters. Since time is quite literally money in this industry, we need to move up from the heavy machinery of the rig floor and step into the driller's cockpit. This is where data becomes king. The driller performs an incredibly delicate balancing act. Honestly, it's a lot like a pilot managing flight telemetry. They're constantly monitoring 4 key parameters. First, there's weight on bit, or WOB, which is exactly what it sounds like, how hard the bit presses into the formation. Too little weight, and you're barely scratching the rock. Too much, and the bit wears out prematurely. Then they have to balance that with rotary speed, or how fast the bit is actually spinning. Next is flow rate, which tracks how much drilling mud is being pumped down the hole. And finally, torque, which is the resistance to rotation. For instance, if the torque spikes, that tells the driller the bit is working way too hard or the string is dragging against the side of the hole. Now, optimizing all of those parameters leads us directly to the holy grail of the entire operation, maximizing ROP, or rate of penetration, without breaking the equipment. ROP is your key performance metric. It's measured in feet or meters per hour, and the math is pretty straightforward. A higher ROP means faster drilling, shorter time spent on the well, and ultimately significantly lower costs. Section 3. The bottom hole assembly. So you might be wondering, what is actually doing the cutting down there? Let's mentally travel from the surface all the way to the very end of that miles-long pipe to think about the hidden hardware. It turns out a drill string isn't just a basic cutter on the end of a long tube. Not at all. It's a highly sophisticated toolkit known as the bottom hole assembly, or BHA. Every single component down there serves a critical function. And it's wild because you're contrasting the brutal, violent forces of crushing rock with incredibly delicate telemetry sensors. Let's break it down. We have drill collars. These are thick, heavy-walled pipes that provide the actual physical mass for the weight on the bit. Then you have stabilizers, which are blade assemblies that keep the BHA perfectly centered. But then we get to the brains of the operation. MWD, or measurement while drilling tools, which give us real-time survey data. Alongside those are the LWD, logging while drilling tools. These actually evaluate the geological properties of the rock, like porosity and resistivity, right as it's being cut. And finally, just in case things go sideways, there's a jar. This is a heavy mechanical tool designed to deliver a massive upward impact to free the pipe if it ever gets stuck. Section 4. Steering the wellbore. Now that we've got our toolkit assembled, we face an absolute engineering marvel. How do you make a straight, rigid steel pipe drill a curved hole? You see, modern offshore wells are almost never just straight vertical drops. Directional drilling allows operators to kick off the vertical plane and hit horizontal targets that are kilometers away. This is a total game changer because it allows them to use a single fixed platform to reach oil reservoirs spread out over massive areas, drastically cutting down the number of surface platforms they need to build. Historically, changing direction meant relying on what's called a sliding mode. In this setup, the drill string stops rotating entirely. Only the bit turns, powered by a hydraulic motor that pushes fluid through a slightly bent section of pipe. The rest of the pipe essentially just slides along behind the bit. It works, but it's slow. That's why rotary steerable systems, or RSS, completely revolutionize this whole process. RSS eliminates all that start and stop friction. It uses an intelligent BHA that continuously adjusts the bit's direction while the entire drill string keeps right on rotating. The result? It's much faster, and it creates a vastly smoother wellbore trajectory. But wait, how do the drillers even know which way the bit is pointing when it's miles underground? Well, down in the MWD tool, you've got accelerometers measuring the inclination or the angle from vertical. You've also got magnetometers acting like compasses to measure the azimuth or the compass direction. But here is the absolutely fascinating part. How does that data actually get back up to the surface? It's converted to binary code and it's transmitted using the drilling mud itself. By creating pressure pulses in the fluid column, the tool sends data miles up to the surface. It is literally like an underwater Morse code. Incredible, right? Section 5. Geosteering and real-time data. All right, we have reached the climax of the operation. This is where we tackle the hardest problem of all: invisible navigation. Think about this for a second. How do you steer a drill bit to stay inside an incredibly thin oil vein when you are 5 miles underground and completely blind? Even with all the 3D surface seismic data in the world, the geometric coordinates are never perfectly accurate. Just a tiny 5% variation in sound velocity during a seismic survey can lead to calculating the target's depth with hundreds of feet of error. So if you're aiming for a thin horizontal oil layer, how do we avoid missing the reservoir completely? The solution is brilliant. You give the drill bit eyes so it can see the rock boundaries in real time. This technique is called geosteering. Remember those logging while drilling sensors we talked about a minute ago? Well, they continuously evaluate the formation and compare the live data against the predicted geological models. They're constantly measuring things like azimuthal resistivity and gamma rays. And because oil-bearing sand and non-productive shale have completely different radioactive signatures, the sensors can quite literally look up to detect the high gamma rays of an overlying shale ceiling and look down to detect the low gamma rays of the sand below. The driller uses this real-time logging to essentially surf the geological boundary. They're constantly adjusting the trajectory to ensure that millions of dollars in oil aren't just completely bypassed. To wrap things up, I want to leave you with this really powerful thought from our source material. Geosteering enables the driller to guide the drill bit to the optimum geological destination rather than a possibly non-optimum geometric location. Navigating to the rock's actual reality rather than just trusting a map's prediction changes everything about offshore efficiency. It really makes you think, if we can use sound waves, magnetic fields, and pressurized mud pulses to surgically navigate the deep, invisible Earth, what other invisible frontiers are we ready to conquer? Keep that in mind the next time you see a rig on the horizon. Thanks for joining me on this explainer, and keep learning.